So hello from Japan. I wish I could be like physically there, but things are not very good here. Yeah, I wish I could see you physically in the near future. So today I talk about program semantics, approaches to program semantics that are inspired, let's say, by linear logic studies. So this is an overview of today's talk. So I will first quickly recall what you've probably seen in this winter school, and then I go on to explain two kinds of program semantics that use linear logic ideas. Okay, so the first one to recall is MELL proofnets, and you've seen probably that these proofnets can simulate lambda calculus, which can serve as a model for functional programming. And there are many, at least a few, famous translations from lambda calculus into proofnet. And then on the left-hand side is what the so-called call by name translation, and on the right-hand side is the so-called call by value translation. So as you can see, the difference is where the bound modality is. In the call by name translation, arguments are inside the bound, whereas in this call by value translation, the whole function type is inside that bank. So I'm showing you two translations of the same lambda term, which is lambda x.x applied to lambda y.y. So these two translations basically look the same without some and then the only difference here is where these dereliction nodes are. Right, and then I think in this winter school, you've seen this call by name translation, but today I'm gonna use this call by value translation for some reasons. Okay, and then once you translate a lambda term into a proofnet, you can further simulate computation using card elimination. So namely, you can simulate beta reduction of lambda terms using card elimination steps. So in this example, we can perform beta reduction one step and then get this result, lambda term. And on the proofnet side, we start with this proofnet and then apply card elimination 4 times, and then we get this proofnet that is actually the call by value translation of this result lambda term. So when you look closer, the first card elimination deletes this box, and then the second one deletes these multiplicative nodes, and then the third and fourth delete or eliminate pairs of an action node and a card node. So in this case, all the card elimination steps are just simplification of the proofnet that we started with. Now we have proofnets and then we have card elimination, and using them together, we can simulate lambda calculus. Now, another thing that you've probably learned in the school is geometry of interaction. So geometry of interaction gives semantics of linear logic proofs and accordingly linear logic proofnets. And what it does is to give invariant under card elimination. And then if we think about simulating lambda calculus, that means that geometry of interaction can provide invariant under beta reduction. And then one characteristics of geometry of interaction is that the invariant can be seen as paths on proofnets. So if we go back to the example we've seen, so this is the sequence of card elimination, 4 card elimination steps that simulate a single beta reduction step. And then what geometry of interaction can give you is a path on each proofnet that kind of survives the card elimination steps. So in the first proofnet, we have a path going from here. I hope you can see the pointer going from here, and then the path goes to the right-hand side of this action node, and then comes down on the other hand, on the other side, and then goes to this box. And then this path changes a bit, but survives through card elimination steps. And then at the end, the corresponding path is just a very simple path here. So this data is what geometry interaction can provide. So in a sense, using geometry interaction, we can give semantics of lambda calculus as well as proof nets. So these are the two things that I wanted to record first. And then combining these two ideas, combining these two ideas is a kind of program semantics that I will call token passing machines. Good. So I'll move on to the token passing machines. So these machines are a class of semantics of function programs where programs are represented graphically, such as proof nets, and then evaluation of a program is modeled by dynamic computation of the invariant provided by GOI, which is the path provided by GOI. And then the dynamic computation actually amounts to passing a special node called a token around the proof net following the path given by GOI. So this kind of semantics was pioneered by Donald and Renier and then Maki as well, with some application to compiler construction. So I will show you how a token passing machine looks like. So this video is taken from my old slide, and then it shows a token passing machine called an interaction abstract machine. Perhaps it is actually jumping abstract machine for those who know well, given by Donald and Renier. So we are trying to evaluate this lambda term. Yep. And then the first thing we do is to translate the term into a proof net like this. And then once we've got a proof net, we let a special object called token, which is the token is indicated by a red triangle here. And then we let the token move around this whole proof net and then compute the path given by GOI. So I can start the video, and then it looks like this. The token starts from here and then move around the proof net. And in the way it moves around, the net can be also described using some beta reduction, but I'm not going into details. Yeah. And then actually this token is following the path given by GOI. And then at some moment it jumps to shortcut. And at the end, so now the token stops here, and this place indicates actually the result value of evaluating this lambda term. So when you look at this, so here, so this box is actually the translation of this lambda term, lambda z.z. So this is how a token passing machine looks like when you run it. So evaluation of a lambda term becomes a token, a special object running around a proof net. So it was pioneered by these guys. And then there are many variants for function programs with computational effects, such as indeterminism, global state, probability, and then even quantum effects. And there's some variants use not just one, but multiple tokens to model certain effects and also parallelism. And there is also an application of a token passing machines to high-level synthesis, where you directly compile a function program into hardware design. Cool. So, am I going too fast? Let's see. So I showed and then briefly explained token passing machines. So the key idea is to pass a token around the proof net. It's very visual, which I like. And then it is also mathematically founded well. so you can use category theory to describe these token passing machines in a compositional way. Okay, but then when you look at token passing machines, you can come up with one natural question. So the one characteristic of token passing machine is that a proofnet you start with never changes. So it's just token moving around and you keep the proofnet fixed. So it is a good characterization that, for example, enables the application to high-level synthesis. But then you can wonder what happens if there can be actually rewriting during the token traveling around the proofnet. So what happens if dynamic rewriting is allowed in token passing machines? So for example, we just speed up token passing by removing overlapping paths. So this is a proofnet that encodes a lambda term that we've seen. And then we can apply one step of cut elimination. And then in this case, we can simplify this proofnet and then get this proofnet with fewer nodes. So we can do token passing on each of the proofnet, and we're supposed to get the same result because these are like equivalent on the using these are bit equivalent. But then, so if we first do cut elimination and then we do the token passing, we're supposed to get the same result. But then what happens if we start with this proofnet, we start token passing on this net, but then in the middle of token passing, we do cut elimination and somehow change this proofnet into this proofnet and then try to continue token passing from there. Does that give the same result, or is this whole process even possible? So that was the question I was asking a few years back. And then answers are, it is actually possible in a principled way. And the way is inspired by actually virtual reduction. And the idea is that the token can witness and control every possible rewriting that we need. And this led to another kind of program semantics inspired by GOI. And then I call this semantics token guided machines. So compared to token passing machine where the token travels around a fixed net, in token guided machines, token travels around the proofnet, but in the middle, it can trigger rewriting. So we're now moving on to the last big part of the talk. So token guided machines have similar characteristics as token passing machines. For example, we still represent programs graphically, typically using proofnets or some other graph. And then evaluation is modeled by token passing, which dynamically computes the dual invariant. But we now add the ability to rewrite graphs dynamically. And then most notably, evaluation strategies can be represented by the way the token travels around. So I'll show you an example. So we're trying to evaluate this lambda term that we've seen before, and the result is going to be this lambda term, this just functional application. And then on the left-hand side, I will show you the token passing machine given by Danos and Renier. And then on the right-hand side, I'm going to show you a token guided machine. So let's first see what happens. So the token travels around, but then in a token guided machine, something happens, and then we see some simplification of a proofnet. And then sometimes it's not simplification, but anyway, at the end, the token stops in the middle of a proofnet. And then in the token guided machine, the resulting proofnet is exactly, in this case, corresponds to the resulting proofnet exactly corresponds to the result lambda term in this case. But on the left-hand side, you can see that the proofnet never changed, right? So maybe we can see it again. So the token travels around in the very same way, following the same path. Oh, sorry. It doesn't go quite well. Right. So the token travels around, and then at some point, the token notices that card elimination is possible, and then does the card elimination. Right. So here a box is eliminated, and then the token keeps traveling around, and then does further card elimination. So in many cases, card elimination is just simplification of a proofnet, but it's not always. So when the token hit a contraction node and then witnesses that card elimination for the contraction node is possible, then some part of the proofnet can be duplicated, like here. So it's not always a simplification, but it's always card elimination steps that we know. And then the token keeps going. And then at the end, we've reduced all the ways through the proofnet and get this translation. Right. And then it was like the motivation, at least for me, to think about token guarded machines was to speed up token passing by simplifying proofnet. But then it turns out that it was independently studied before, that token guarded machines can model variants and can model different evaluation strategies in a very simple change. And also there's an application of these machines to prove observational equivalence between programs. So I will explain these one by one. So firstly, the important feature of token guarded machines is that we can just amend the way the token interacts with nodes of a proofnet and represent different evaluation strategies. So this stuff was actually first started by Sino, who was a student, I think, of Maki. And then he used interaction nets instead of proof nets. But if you know it, these are this can represent the same thing regarding translation of the lambda term. And then later on, I came to the same idea and then developed a machine that can evaluate lambda characters with different strategies. So I want to show you a demo of the token guarded machine I developed, and then the machine actually uses what I call lambda graph like this instead of a proofnet. So this graph is in a sense modification of a proofnet so that it better matches syntax tree of the lambda term. So if you you can see all the boxes are inherited, and you can also see this dereliction node, which was previously here. And in this application is like the combination of these stuff and so on. So this par node is like a lambda node that represents function application. So I briefly stop sharing and share a different screen. What is that? I hope that's okay. Yep. Can you see the shared screen?
We can see it.
Thanks. So you can hit there's a link on my webpage to this online visualizer, so which works on the browser. So you can type in any lambda term you want. You can type in untyped lambda term because this tool doesn't do type checking. And then you can select evaluation strategy. And then when you select the call by name, this tool actually shows you what the token passing machine does. So here's the translation of the lambda term. And then when you hit the start button, the token, which is indicated by a red line, travels around manipulating some data it carries, and then it stops here. But then with the same lambda term, we can switch to a different evaluation strategy, for example, called by value evaluation strategy. And then as you can see, the translation is almost the same, except for this label here. So the change of the label exactly reflects the change of evaluation strategy, and then it changes the way the token interacts with this node that represents function application. So we can again let the token move around, but now the token does rewriting on its way. And stops. And then now we can see that this graph is actually the translation of lambda z, which is the result we wanted. And then we can also change the lambda term. There are some built-in examples. So here is an example that shows you the difference, that shows you better the difference between evaluation strategies. So we apply this function that discards its first argument to the lambda term that diverges. So if we, for example, evaluate this term with the call by name strategy, because the first argument x is never used here, the evaluation never goes on to this diverging term. So the call by name evaluation of this whole lambda term should terminate. And then indeed, if we run this tool with a call by name evaluation mode, the token just travels around and stops here, which is how a token passing machine would behave. But then we can switch to call by need. And here the token does some rewriting, and it arrives at this subgraph that represents actually this part of the lambda term. So and also the point is that this run terminates. And now we can switch to the call by value mode. So the question is, what will happen? So when we evaluate this lambda term with the call by value strategy, we have to evaluate this part, and the evaluation is not gonna terminate. And then you can exactly see the divergence here. So the token travels around, does some rewriting, and then from now on, it actually never stops. So if you look at it for a while, you might notice that we are actually looping. So on this side, we only have a few steps of rewriting, like applied happening repeatedly. So it's not gonna end. It will only warm up your laptop, like I'm doing. So I'm gonna stop here. Good. And then there's another version, which is right to left called by value. So you can play with this tool if you want, typing in any weird lambda term. Cool. So I'm going back to my slides. Right. And then, so it was to demonstrate how token garden machines can model different evaluation strategies. And there's also an application to proving observational equivalence using these kind of token garden machines. So the point is that because the token rules everything, we can analyze program evaluation by inspecting the token locally. So we can analyze these kind of things. What happens to a certain part of the program during evaluation, and how a term interacts with the context. So these are kind of questions that we have to ask when we try to prove observational equivalence. And what enables this local analysis is the characteristics of token-guided machines that evaluation strategies are represented so handily by the token. And also part of a program, when we think about it, can be represented as subgraphs. And then subgraphs are actually more expressive than subterms because we can collect all parts of a program that refers to the same variable and represent them as a single subgraph, which we can't with terms. So it was a very brief explanation, but this, and then I was studying this local analysis in my PhD. Good, so I'm gonna wrap up. So there were some further research questions. So for token-guided machines, the machines I showed actually apply rewriting as much as possible. But we can think of some flexible rewriting where the token can choose not to rewrite the graph. And by this, we can expect that the space and time efficiency can be balanced in a good way. So this is one question. And another question is to further study the application to observation equivalence and then think about programs with computational effects. So this is kind of an ongoing work for me. And then the third point is to transfer insights that we've got with the studies of token passing and token guided machines to conventional syntactical semantics like abstract machines and reduction semantics. So there's already a series of work by Akatori and his colleagues on syntactical token passing machines, which you might want to look at. So yeah, that's it. Thank you.
Thanks a lot, Koko. So we have time for maybe one question, maybe two. I say one. No question. Well, I have one.
Good.
At the beginning, it was not very clear to me what reducing the net during token passing was bringing to the picture. That was different from first doing cut elimination and then having the token travel through the net. Am I correct in assuming that it is necessary to interpret evaluation strategies that are different from the standard ones, as you showed us in the last part of the talk?
I'm not sure it is absolutely necessary, but yes, in my experience, it was very useful. For example, with this dynamic rewriting, we could finally model call by need evaluation using token passing.
Okay, thanks. So, well, we can thank Koko again.